Hi, everybody. Last time we were talking about sketching spectra going from the structure to the spectrum. And one of the things that we mentioned then was that when you're trying to do an exercise like this, you're at a terrible disadvantage unless you've memorized the NMR chemical shifts. Now, I'm not expecting you to memorize any NMR chemical shifts. What I would like for you to do is go to a table of NMR chemical shifts, and that can be your guide. So you can either find one online, or what I'm suggesting is on the exams and quizzes and so on, I've prepared this table of NMR chemical shifts. And so I put this on the course website, and it is indicating the proton in boldface, and then it tells you what the chemical shift is. So, you can you can Google a table of NMR chemical shifts, or you can use this one that I put on the course website. And when it comes time to taking exams and quizzes based on NMR, I'll show you this table. I guess you can use another table, but some of them might have a lot more information than you really need, and they can be difficult to interpret. You can, but this will be a good guide for the chemical shifts. Okay, so let's continue talking about, let's do one more problem where we're going from a structure and sketching the NMR spectrum of that compound. All right, so what if we want to sketch the NMR spectrum of this compound here? Okay, so first off, we need to know how many signals. So how many signals are we going to get here? Can you tell me in the chat what your guess would be? How many signals? Okay, so let's see, some people are chiming in. Uh-oh. All right, so there are going to be 5 signals. So there's a proton, that's 1. This is the first signal here. There's a proton here, can't forget about him. These 3 protons over there. There's a CH2 group, and the 2 protons of the CH2 group in this case will be equivalent because there's no chirality center in the molecule, so they're equivalent. And then we have another methyl group over there. So it's 1, 2, 3, 4, 5 signals. Yes? Okay, so now let's talk about the splitting. And remember, yesterday we were talking about n+1 splitting, where n is the number of neighbors. You can think of it that way. N is the number of neighbors that a proton has. But remember, those neighbors cannot be, those neighbors have to be 2 bonds or 3 bonds away. And those neighbors have to be not equivalent to the proton under observation. In other words, the proton whose splitting pattern we're trying to understand and predict. And remember that those neighbors must all be equivalent to each other. Okay, so let's go with this guy here. What's going to be the splitting of this guy here? I need a word that ends in "et." Tell me in the chat. This proton right here, what's its splitting pattern going to be? We're thinking about n+1 splitting. all right? It's going to be a doublet, right? Because there's another proton 3 bonds away, and these 2 protons aren't equivalent to each other. N equals 1, 1 plus 1 is 2. Okay, what about this guy here? What's his splitting pattern going to be? This next one over. All right, this next one over, this is going to be another doublet for the same reasons. What about this methyl group up here? What's his splitting pattern going to be? Okay, tell me in the chat, this methyl group here, what's his splitting pattern? All right, that's going to be a singlet because the 3 protons of a methyl group are always equivalent to each other. So each of these protons is 2 bonds away from another proton, but that proton is equivalent to the one under observation, and there are no protons, other protons 2 or 3 bonds away that aren't equivalent to these methyl protons. Okay, now this methylene group, the CH2 group, what's going to be the splitting pattern here of the CH2 group? All right, that's going to be a quartet. And finally, this methyl group over here, his splitting pattern will be this methyl group over here. What's the splitting pattern going to be? N plus 1. N is the number of non-equivalent neighbors. Yep, that's going to be a triplet. Okay, because these protons are 3 bonds away from 2 other protons, N plus 1, N equals 2, 2 plus 1 is 3. Okay, so now we can now we can sketch the spectrum. And like I said before, it's not an easy thing unless you've memorized the NMR chemical shifts or are looking at a table of NMR shifts. Okay, so I have this little table here that I put on the course website, and one of the entries that I see on this table is that an aldehyde proton absorbs at about 10 ppm, right? Where am I getting that from? I'm looking at a table of NMR chemical shifts, and this guy absorbs at about 10 ppm. So I'm going to put a doublet at around 10 ppm, and the doublet is 2 lines of about equal size. So let's see, I'm going to call this guy A. I'm going to call this guy B. I'm going to call these guys C. I'm going to call these guys D, and I'll call these guys E. So this is protons A. Okay? All right. And so now another thing I see, and again, this is something that I'm just getting this from the table. Can move off the table in a second. I'm looking this at the table, and I see that an alkene proton absorbs somewhere between 4 and 7 ppm. So that's a pretty wide range, right? And so now the question is, well, am I going to put it near 4, or am I going to put it near 7, or in between, or is it going to be at the extremes, or what? Well, you see, this proton is pretty close to this oxygen atom. It's 1, 2, 3 bonds away from an oxygen atom over here. It's 1, 2, 3 bonds away from another oxygen atom here. And this proton is also close to the second multiple bond. So if an alkene proton, according to my table, is somewhere between 4 and 7, I'm probably going to put it close to, well, maybe 6, something like that, right? I don't expect you to come up with the chemical shift with 2 decimal point accuracy, right? Just something that is reasonable and in that range, maybe plus or minus 1 ppm, right? I'm not looking for double-digit decimal point accuracy. So an alkene proton, because it's close to that multiple bond, is somewhere between usually 5 and 7. So this one's pretty close to electronegative atom. It's pretty close to another multiple bond. I'm going to put it at around 6. And it's going to be a doublet at about 6. And so, see, this was a 1 hydrogen signal. So this other doublet, when I sketch it out, I'm going to make it about the same size as the one I drew before, right? Okay, so now that's B. Okay, so now of all of the remaining protons, the C, the D, and the E, who is going to be most upfield? Tell me here in the chat. Who's going to be the most upfield of the remaining protons, the D, the C, the D, and the E? Who's most upfield? Yeah, it will be E, because E is farther away from any of these double bonds, and it's farther away from the electronegative atoms. And so I'm looking at my table and I see that a hydrogen that is more than about 3 bonds away from an electronegative atom, that's at about 1 ppm. Right, so it's not at 0 because that's where TMS is. So this signal I'm going to put at about 1 ppm, and it's going to be a 3 hydrogen triplet. So you see, this peak represents 1 hydrogen. So this next signal I'm going to draw is I'm going to try to make it 3 times bigger than this one, because that upfield triplet comes from 3 protons. So at about 1 ppm, just eyeballing it, I make a 3 hydrogen triplet at around 1 ppm, right? Okay, so that will be the E protons. Okay, D, D and C. Who's more downfield, D or C? Tell me here in the chat. I need to find a home for C and D. So which one is going to be more downfield? Or which one's going to be, let's say, which one's going to be more downfield, the C or the D? Yeah, D is going to be more downfield because D is closer to electronegative atom. And on my table, what I'm getting is that proton is going to be somewhere around, maybe around in the 3s. Okay, so maybe somewhere down here, I'm going to put a quartet, right? So this signal is 1 hydrogen. This one I'm going to make 4 times bigger. Maybe 4 times bigger. And it's going to be this quartet somewhere in the 3s like that. All right, so that's the D proton. And now this guy here, according to my table, he's somewhere in the 2s. So I'm going to have a 3 hydrogen singlet over here in the 2s. So that's the C proton. And so that would be my sketch of the NMR spectrum of this compound. So it's 2 doublets, a quartet, a singlet, and a triplet. Okay, so now let's look at the actual spectrum and let's see how we did. Oh, we did damn good, right? We have the right number of peaks and they're in the right order. Because I'm just guessing from a table of chemical shifts, I'm not expecting 2 or 3 decimal point accuracy, just sort of in a reasonable range. Okay. All right, so now it's time to get to the big enchilada, what all of our discussion about NMR has been leading to, and that is going from a spectrum to a structure, right? So everything we've been talking about NMR has led up to this moment. Is we're going to be given an NMR spectrum, and then I'm expecting you to be able to come up with the structure of the molecule. Okay, so let me give you the step-by-step. Okay, so we have spectrum to structure. Okay, step number one, what you do is you calculate the DOU from the formula. Remember DOU, degrees of unsaturation, and remember that formula for the DOU, which is equal to 2 times the number of carbons plus 2 minus the number of hydrogens minus the number of halogens plus the number of nitrogens all divided by 2. So this is going to tell you how many rings or how many multiple, the total sum of rings and multiple bonds, right? A ring eats up 1 degree of unsaturation, a double bond eats up 1 degree of unsaturation, a triple bond eats up 2 degrees of unsaturation. Okay, so calculate the DOU or else you'll be DOA. Then, step number 2 is that sometimes, not all the time, but sometimes we have functional group evidence. So this will be from an independent experiment. Usually, maybe it's from an infrared spectroscopy experiment, or we'll know that, well, it's a ketone, or it's a carboxylic acid, or it's an ester. We'll have some kind of functional group evidence if we're lucky. So sometimes yes, sometimes no for step 2. Okay, now step number 3, this is the killer, right? This is the hard step, is that now what you want to do is you want to draw fragments, little pieces of molecule that fit the spectrum in terms of chemical shift, integration. This is integration. This just means the number of hydrogens that are giving rise to that signal. And so this information will be given. Fragments that fit the chemical shift, the integration, where you'll be told how many hydrogens are responsible for that signal, and then the splitting. Right, and the splitting is telling you how many neighbors there are in the compound, how many neighboring carbons, how many neighboring protons there are neighboring the proton under observation. Okay, that's very hard. Step number 4 is link the fragments. And you've solved the structure. Okay, so that's the step-by-step, kind of deceptively simple. Let's work some examples. Okay, so C7H14 ClNO. That's the formula of the compound. And from independent evidence, we know that this is an amide. Right, someone got into the lab and figured out that it was an amide. Okay, and so now down here, I'm going to sketch the spectrum. Oh dear. Okay, so this spectrum goes from 0 to 5 ppm. Right, so that's the chemical shift. I can't get my head out of the way here. So that's the chemical shift in ppm. All right, and at a little bit beyond 1 ppm, I see a triplet. And yeah, I see a triplet. And this guy is worth 6 hydrogens. So that's the integration. So 6 hydrogens are giving rise to that signal at about a little bit past 1 ppm. And then at about 2.5 ppm, I see another triplet. At 2.5 ppm, I see another triplet. And the integration here is 2 hydrogens. So 2 hydrogens are giving rise to that signal. Okay, 1, 2, 3, a little bit past 3 ppm, I see a quartet. I see a quartet, and this quartet is a 4 hydrogen signal. So 4 hydrogens are giving rise to that signal. And then finally, let's see, 1, 2, 3, 4, a little bit close, near 4 ppm, I see another triplet. I see another triplet, and that triplet is a 2 hydrogen signal. Okay, so now do all of these numbers add up to 14? Hope so. Yeah, they add up to 14. So that's the integration. It's just telling you how many protons are responsible for each signal. Okay, so let's go through the step by step. The DOUs here are equal to what? What's the DOU of this formula? Tell me in the chat. Isn't it 1? 7 times 2 is 14, plus 2 is 16. 16 minus 14 is 2. 2 minus 1, chlorine is 1. 1 plus 1 nitrogen, we're back to 2. 2 divided by 2 is 1. So this thing has 1 DOU. All right, so now we can write our first fragment because we know that it's an amide, right? And so we know that the amide has a carbon-nitrogen double bond, a carbon-oxygen double bond, so that we've taken care of our DOUs. So there's our first fragment. We're into step 3 now. We're drawing the fragments. Okay, so now for to proceed, my advice to you is when you're doing problems like this, to start with the most upfield signal or with the most downfield signal. Because you get these are usually the ones that are easiest to interpret, and they're the signals that you're going to get the most mileage out of. Okay, so that would be my advice to you. Start analyzing the most downfield signal or start analyzing the most upfield signal, right? Don't jump around from one signal to the other. Start upfield or start downfield. I'm going to start upfield. So that's a 6 hydrogen signal. What fragment could that be that corresponds to 6 hydrogens? Tell me in the chat. Is it a carbon atom with 6 hydrogens stuck to it? Is that a viable possibility? What piece of molecule, what fragment of molecule could give me could give me total up to 6 hydrogens. Any suggestions out there? 6 hydrogens? What could that possibly be? Is it a carbon atom with 6 hydrogens stuck to it? Oh, it could be 2 equivalent methyl groups. 2 equivalent methyl groups, and that adds up to 6 hydrogens. Is that the only thing it could be? Oh, heavens, no. It could also be 3 equivalent CH2s. Is that the only thing it could be? No, it could be 6 equivalent CHs. The key there is adding up to 6, 2 methyls, 3 CH2s, or 6 CHs. And the other key there is that it is they must all be equivalent to each other. So maybe you've taken philosophy courses. Maybe you've heard of a fellow named William of Ockham. And he was a medieval philosopher, and he came up with what is called Occam's razor, which says that given multiple possibilities, the simplest one is usually right. I don't know if I agree with that, but that is a useful point of departure. So this could be 2 methyls or 3 CH2s or 6 CHs. Everything, all of those protons are equivalent to each other. I'm going to go with 2 equivalent methyl groups. Okay, so what I'm going to do is I'm going to draw those two methyl groups, and I'm going to draw them in such a way that I'm reminding myself that they have to be equivalent to each other. And whatever I do to one methyl group, I have to do to the other methyl group. So I'm going to draw here on my piece of scratch paper, I'm going to draw a CH3 like that, and I'm going to draw a CH3 like that, and I have to remind myself that whatever I do to one of these methyl groups, I have to do to the other methyl group because I have to keep them equivalent. Okay, so we've taken care of the integration, the 6 hydrogen, right? We had 3 possibilities. I'm going with the simplest one. Now, let's take care of the splitting. This is a triplet. What is that saying about who lives here? Tell me in the chat. This is a triplet. Who lives here? This is split into a triplet. What lives here? Not 2 hydrogens, 2 CH2s, right? It's not going to be 2 hydrogens here. It has to be hydrogens on carbon, 3 bonds away or 2 bonds away. And so that's what's going to give me the methyl group. So yeah, that's what the splitting is telling you, that this guy must be next to a CH2. But whatever I do to one of these methyl groups, I have to do to the other methyl group because I have to keep them equivalent. Okay, so I did that. Now, let's take stock. There better be a 4 hydrogen signal somewhere in the spectrum, or else what I've come up with is pure rubbish, right? These 2 methyl groups, there better be a 4 hydrogen signal somewhere in the spectrum. Is there? Yeah, here he is, right? It's a 4 hydrogen signal. That means 2 CH2s. And because it's 4 hydrogens, I see now that these methyl groups are also equivalent to each other, right? So these methyl groups are equivalent. These CH2 groups are also equivalent. So now I'm focusing on this signal for the moment. What is the chemical shift telling me about these CH2s? Look where it is at around past 3 p.m., 3 ppm. Tell me in the chat, what is the chemical shift of this 4 hydrogen signal telling me? Why is it down past 3 ppm? Why isn't it near 1 ppm? What's the chemical shift telling me about this thing? Any guesses out there? I have a 4 hydrogen signal at around 3 ppm, past 3 ppm. It's closer to an electronegative atom. Sure it is. And which electronegative atom could it be? The nitrogen. Right? It can't be the chlorine, because then I'm going to run out of bonds. I can't put a Cl here, right? Because chlorine never can't put a Cl here, because then I won't have any place else to put anything else. So the downfield chemical shift of this signal is telling me it's close to an electronegative atom, and the only electronegative atom that is going to fit is if that CH2 group and if this CH2 group are next to this, close to that nitrogen. Okay, so making good progress here. We've taken care of him, we've taken care of him. All right, now let's go to the most downfield signal down here. It is a 2 hydrogen signal. So what is the integration saying? That's 2 hydrogens. It could be a CH2, or it could be 2 equivalent CHs. All right, I'm going to go with the simpler alternative, that this is a CH2. Look at the downfield chemical shift of this at around 4 ppm. What is the, well, not the shift. Let's look at the integration. I mean, not the integration, the splitting. It's a triplet. What is that telling you about who lives here? Who has to live here? This is a triplet. Who has to live here? Okay, tell me. Who has to live here? It's a triplet. This signal here, that's that one, the most downfield signal. Who lives here, so that this is a triplet? Another CH2, exactly. Okay, so now let's take stock. We're looking for a home for 7 carbons. 1, 2, 3, 4, 5, 6, 7. All of our carbons are there. We're looking for a home for 14 hydrogens. 5, 10, 11, 12, 13, 14. All of our hydrogens are there. We're looking for a home for a nitrogen, an oxygen, a chlorine, and 1 degree of unsaturation. So the structure of this compound has to be, there's a Cl there, right? And this is a downfield chemical shift because this CH2 is next to this Cl, and this bond gets hooked up to that one. There's our structure. All right, now this molecule, the way I've drawn this here, this looks like something that maybe Dr. Seuss would come up with. So maybe in this little box down here, I'm going to just draw a prettier picture of what this thing would look like. And so this guy, a prettier picture, that would be the structure of the compound. This is what all of our NMR has been leading up to, is being able to come up with the structure from the formula and the spectrum, right? This isn't that easy, right? This is pretty hard. And the only way you're going to get good at it is by practicing it. Okay, let's try again before time runs out and we have to do the quiz. C11H12O2. C11H12O2 And we have from infrared evidence, we know that this has the carbon-oxygen double bond. Okay, and so now let's make a sketch of the spectrum here. So this one goes 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And the most downfield signal at around 8 ppm is this one hydrogen doublet down here. And then in the 7s, you have a mess. You have a mess that looks like that. It's just a jumble of lots and lots and lots of peaks. Okay, and this is worth 5 hydrogens. Okay, and then at around in the 6s, you have another doublet, and that's worth 1 hydrogen. That's the integration. And then at 1, 2, 3, 4 ppm, there's a quartet. And that is worth 2 hydrogens. And then the most upfield signal at about 1 ppm is a triplet. And this is worth 3 hydrogens. Okay, so let's figure out what the structure of this guy is. All right, how many DOUs? 11 times 2 is 22 plus 2 is 24. 24 minus 12 is 12. 12 divided by 2 is 6. So this has 6 DOUs. Wow, that's a lot. But anytime you have 4 or more DOUs, what are you hoping and praying for? Tell me in the chat. This has 6 DOUs, but I'm giving you this little clue here that anytime you have 4 or more DOUs, what are you hoping and praying for? 4 DOUs. 4 or more DOUs. What are you hoping that that structure has? Yeah, you're not hoping and praying for 4 rings. Heavens no, that would be an extremely complicated structure. You're on the right track with the ring, but what kind of ring is going to eat up 4 DOUs? Benzene. Exactly, the benzene ring. So whenever you have a spectrum that has 4 or more DOUs, you're hoping and praying for a benzene ring. Well, your prayers are answered here because I'm looking at my table of NMR chemical shifts and I see that in the 7s, that's where protons on benzene occur. So I can draw my first fragment. Right, that has 4 DOUs and there are 5 hydrogens in the arene region of the spectrum. Okay, so I've just taken care of 4 DOUs of my 6 DOU formula. All right, that's 4 DOUs. I also see that I have a carbonyl group in it, the carbon-oxygen double bond. I've taken care of 5 DOUs. Okay, so now let's go upfield. It's a 3 hydrogen triplet. So what is going to give me a 3 hydrogen signal? It's going to be probably a methyl group, a CH3, right? It doesn't have to be that, but that's just the simplest explanation. Another thing is that what is the splitting telling you about who lives here? Who lives here? This is a triplet. This signal is a triplet. So who lives here? Well, that's going to be a CH2, right? And now there better be a 2-hydrogen signal somewhere in the spectrum. Is there? Yep, here he is. Right, this 2-hydrogen signal is split into a quartet. It's exactly what we expect when the CH2 is next to a CH3. What is the chemical shift telling you? The chemical shift here is telling you what? This guy is this one. What's the chemical shift at around 4 ppm telling you? It must be next to an electronegative atom, which is going to be the oxygen, right? And oxygen forms 2 bonds. Let's take stock. How many carbons are we looking at? We're looking at 5, 6, 6, 7, 8, 9 carbons. We're only looking for 2 more carbons. We have all of our oxygen there. So right now we're looking for 2 more carbons and 1 more degree of unsaturation. And so these 2 guys, if I look at my table of chemical shifts, these are in the alkene region of the spectrum, right? And so we need 1 more degree of unsaturation. We need 2 more carbons. How are we going to take care of all of that in one fell swoop? An alkene. So now I'm looking at a lot of the pieces of my puzzle. 6, 7, 8, 9, 10, 11 carbons. All of the carbons are there. All of the degrees of unsaturation are there. All I have to do now is hook them up. So this guy could go there. This guy could go there. This guy could go there. And I'm looking for 2 more hydrogens in the alkene region. There's the structure, right? But once again, it's written kind of in an ugly way. So if I wanted to make this a prettier drawing, that would be the structure of the compound. Okay, so definitely not easy, right? But if you look at my lecture notes online, I have lots and lots and lots of problems for you to work on. Let's see, what are people telling me in the chat? Nothing. Okay. So how about we get to the quiz now? Over the weekend, I'm going to prepare a study guide for next week's quiz, and next week's quiz will be all about NMR. And on Monday, continue doing problems like this where we're solving the structure from the spectrum and the formula. And then next week, we're also going to get into finish up talking about NMR, maybe 1 more lecture on Monday. All right. So now it's time to turn our attention to the